So I'm looking at the questions in chapter 18 in your books. At the end of the chapter, there are a selection of exercises on pH calculations. So I'm going to do a few examples of them, starting with, we'll say question 2. Question 2 says, calculate the pH of the following solutions whose hydrogen ion concentrations are as follows. So first of all, I'm going to look at part B. Part B says that the hydrogen ion concentration of this solution is 4 by 10 to the minus 3. Now I know what the pH is. The pH is minus the log of the hydrogen ion concentration. So therefore the pH in this case is minus the log of 4 by 10 to the minus 3. I put that into my calculator and I get a pH of 2.4. The next one I'm going to do is part E. Part E of that question tells me the hydrogen ion concentration of a solution is 8.7 by 10 to the minus 11. So I know that the pH of anything, and this is your definition for a pH. If you're asked to define pH, you can just write this sentence down. So pH in this case is minus the log of 8.7 by 10 to the minus 11. And when I put that into my calculator, I get 10, pH 10. Right, so that's the first type. Now, the second type is question 3. I'll do 2 of those. So the first part of question 3 says, calculate the hydrogen ion concentration of the solutions whose pH values are as follows. So in the first one, you're given a pH value of 5.65. Okay, to find the pH, you know that the pH is minus the log of the H plus concentration. The pH in this case is 5.65, so that's minus the log of the H plus concentration. If I bring over that minus to the other side, so minus 5.65 is equal to the log of the hydrogen ion concentration. Now, in order to do this, I'm going to get the antilog of minus 5.65. And to get the antilog, it's second function log in your calculator. So the antilog of minus 5.65 is equal to the hydrogen ion concentration. And when you put that in, you get 2.2387 by 10 to the minus 6 is the hydrogen ion concentration. So the H plus concentration is equal to that. Part E, I'm going to look at part E. Part E says, find the hydrogen ion concentration of a pH, a solution whose pH is 9.65. So we know that the pH is minus the log of the hydrogen ion concentration. That means that 9.65 is equal to minus the log of the hydrogen ion concentration. So I'm going to bring over that minus, so minus 9.65 equals the log of the hydrogen ion concentration. If I put this into my calculator now, this is antilog, which is the second function log of minus 9.65 is equal to the hydrogen ion concentration. And when I put that in, I get 2.238 by 10 to the minus 10 is equal to the hydrogen ion concentration. Now, you can see here that the hydrogen ion concentration is very, very low. Look, 10 to the minus 10. Compared to this one, 10 to the minus 6. The hydrogen ion is very, very low, the hydrogen ion concentration, because it's a base. So look at the pH. The pH is over 7 here, and the pH is under 7 there. So that's an acidic solution, a basic solution. Low hydrogen ion concentration for this one, high hydrogen ion concentration for that one. Okay, now I'm going to look at question 4. Question 4 says calculate the pH of the following solutions. So the first one, it says you've got a 0.1 molar HCl solution. Find its pH. Okay, the first thing I do here is I write down the dissociation equation for HCl. So it's a strong acid. It fully dissociates in solution, fully breaks up into its ions. And this tells me that 1 mole of HCl produces 1 mole of H pluses. Now that's very important that you do that at the beginning. Now your pH, of course, is minus the log of the hydrogen ion concentration, which is going to be minus the log of 0.1. And when I put that into the calculator, you just get that pH is equal to 1. Okay, so that's the first one. Now, part B. Part B of that question. I'm just going to continue on now with this. Part B. Still doing the same kind of thing. Part B of the question, you're given a 0.01 molar H2SO4 solution. Find its pH. Step 1, write down the dissociation equation. So it's a strong acid, it fully dissociates. So you get 2 H pluses plus SO4, 2 minus. So this tells me that 1 mole of acid produces 2 moles of H pluses. Okay, that means that my pH is minus the log of H plus concentration. In this particular case, I had 0.1 mole, so 0.01 moles is going to produce twice as many H pluses, 0.02 moles of H pluses. So my pH is minus the log of 0.02. And when you put that into your calculator, you get a pH of 1.699. Okay, part C of that question. I'm still staying with question 4, part C. We're told that this particular solution has 12 grams of nitric acid, HNO3, in 500 centimetres cubed. So you've dissolved 12 grams of nitric acid in 500 centimetres cubed. Find its pH. Okay, write the dissociation equation. So it fully dissociates into its ions, so 1 mole of nitric acid gives me 1 mole of H pluses. Okay, let's go and find out now how many moles of H pluses we have. 'I've got 12 grams in 500 centimetres cubed. So the number of moles is 12 divided by the relative molecular mass of nitric acid, which is 1 for the hydrogen, 14 for nitrogen, 48 for the 3 oxygens. So this gives me 12 over 63. So that's 0.19 moles in 500 centimetres cubed. So let's convert that to molarity, because concentration is moles per litre. So I'm going to say the molarity is equal to the number of moles divided by the volume in litres, which in this case is 0.19 divided by 0.5. So this is 0.38. So 0.38 moles of nitric acid will give me 0.38 moles of H pluses. So the pH is equal to minus the log of the H plus ion concentration. So that means the pH is equal to minus the log of 0.38. And when I work that out, I get 0.419. Now I'm going to look at part E. Part E, which says find the pH of a solution that contains 5.8 grams of sulfuric acid in 250 centimetres cubed. Step 1, write the dissociation equation. Sulfuric acid breaks up into 2 H pluses and SO4, 2 minus. So 1 mole of H2SO4 gives me 2 moles of H pluses. Let's go and find out how many moles we have. So 5.8 grams divided by the relative molecular mass will tell me the number of moles. The relative molecular mass of sulfuric acid is 98 when I add them all up. So that means I have 0.059 moles of sulfuric acid in 250 centimetres cubed. Okay, so if I want to find its molarity, I'm going to say the molarity is the number of moles divided by the volume in litres, which is 0.25. And that gives me 0.237. So the pH in this particular case then is minus the log of the hydrogen ion concentration, which in this case is minus the log of 0.23237. And when I put that into my calculator, I get 0.324. Okay, so that's question 4, different examples. Let's do the same now with bases to see how this works. So, in question 5, the first part says, find the pH of the following solutions. So the first one, I'll do 3 of these. The first one is 0.95 molar NaOH. So step 1, write the dissociation constant. So NaOH splits up into the dissociation equation, sorry. So this tells me that 1 mole of NaOH gives me 1 mole of OH minuses. I'm not interested in that. So this means the pH, because it's a base, I'm getting the pOH. The pOH is equal to minus the log of the OH minus concentration. So this is going to become minus the log of 0.95. And when I work that out, I get 0.223. That's my pOH. pH is equal to 14 minus pOH. So this is going to be 14 minus 0.223, and I end up with a pH then of 13.977. So don't forget to do this last line here. For a base, you must subtract it from 14. Part C says find the pH of a solution of 1 gram of NaOH in 500 centimetres cubed of solution. Write the dissociation equation. It splits up into Na plus OH minus. Okay, that means that 1 mole of NaOH gives me 1 mole of OH minus. So let's see how many moles we have. I'm going to divide mass by relative molecular mass, which is 40 for sodium hydroxide. That gives me 0.025. I must convert that to molarity. So this is 0.025 divided by the volume in litres. 500 in litres would be 0.5. And when I work that out, I get 0.05. So my pOH is going to be minus the log. So 1 mole of base will give me 1 mole of OH minuses. Put 0.05 moles of base will give me 0.05 moles of OH minuses. So I'm going to get minus the log of 0.05, and when I do that, this becomes 1.301 when I hit that into the calculator. The pH is 14 minus 1.301, and that's going to give me a pH of 12.699. Again, don't forget this line here, subtract it from 14. And finally, part E, I've got 0.37 grams of calcium hydroxide per 500 centimetres cubed of solution. So let's write the dissociation equation. Calcium hydroxide will split into 1 calcium ion and 2 OH minuses. That means 1 mole of this gives me 2 moles of OH minuses. I'm told that I've got 0.37 grams in 500, so let's convert that 0.37 grams to moles. Mass over relative molecular mass, which is 40 plus 2 16s is 32 plus 2 hydrogens. So when I work that out, I'm going to get 5 by 10 to the minus 3. I'm going to convert that now into molarity. So molarity is equal to moles divided by the volume. The volume is 500 centimetres cubed, so that's going to be 0.5, which means that molarity is equal to 0.01. Okay, so 0.01 moles of calcium hydroxide will give me twice as many moles of OH minuses. So the number of moles I have here, therefore, is 2 0.01s. So that's going to give me 0.02. Okay, so my pOH is equal to minus the log of the OH minuses, which is going to be minus the log of 0.02. And when I put that in, I get 1.699 into my calculator. And then the pH is 14 minus 1.699. And that gives me 12.3.